using this expression, and these two expressions. So using these, we can get expression for 1 over u outside and 1 over u inside. So write these expressions. This gives us the overall resistances. You see that UO and UI are coefficients, heat transfer coefficients. So the inverse of them are resistances. So it will give us the individual resistances. Please write it down yourself, and then I'll write it down after that. We already got these numbers, so I'll just doing it myself. AO outside area is so AO is 2 pi ROL. This is 2 pi RIL. So this 2 pi L cancels, 2 pi L cancels from here, 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 2 pi L cancels from here. Here also same, 2 pi L cancels from here. Okay. So we can yes, All right. So now here we have RO. So we can multiply both sides by RO. So we can multiply both sides by RO. This RO is gone. Here we have one RO. We have RO here. We have RO here. We have this RO cancels. We have RO here. Okay. Here we multiplied by RI. So we multiply here by Ri. So this is Ri and this is Ri. This is Ri. Here Ri cancels. RO cancels. So this is a clean expression for the overall resistance, and you can see that overall resistance, this is outside resistance plus inside resistance scaled by Ri over Ro. This is the K2, that is the resistance because of the insulator. This is the resistance because of the metal one. Similarly, when you have 1 by Ui, so you have 1 by Hi alone, and 1 by Ho is scaled Ro by Ri, and then similar we have this resistance because of the insulation and resistance because of the metal one. So this is the overall resistance for cylindrical system. So you already have seen such overall resistances for rectangular coordinate. So now we are ready to solve the problem. Any question to the overall resistance? I think you are familiar. Just we are going through because it's very important. Any question on overall resistance? Okay, so now you then open the tutorial and start solving the problem. Which problem is that? This is tutorial 1. Problem number 4. Problem number 4, tutorial 1. And we also keep your textbook handy, okay? So keep this Impropera DeWitt handy so that we can look at the charts, values, etc. as and when required. So everyone has a textbook with you? Anyone who is not having? See, for this class, you need the textbook, you need calculator, you need copy, you need pen. Okay, all right. Please go ahead with problem number 4. So, what is the first step? Adarsh Kumar. What is the first step for problem solving? Rakesh. Shayan Haldar. Shayan. Siddharth. Okay. What happened? Where is Pratik Kumar? Adrija Roy.
Yes, sir. Yes, sir.
Okay. So, what is the first step you will do?
So to understand the problem and to draw a schematic.
Exactly. So, draw a schematic, and if I call your name, please show the schematic. So, also turn on the camera when I call your name, not now.
Okay, sir.
So, Anik Mondal.
Yes, I'm here.
Okay. Shayan Haldar, what happened? I am calling you for some time. Shraman Pal. Okay, when you do this problem, let me do a roll call.
So was I audible when I said yes, sir?
Shravan Pal.
Yes.
No, you are not audible that time. So is that happening to many? Shayan Haldar, what happened to you? Shahrukh Mandal. Suresh Meena. Rahul Kumawat. Pratik Korane. Pooja Sharma.
Yes, sir.
Okay. Jay Dutonde. Ayush Surana.
Sir?
Ayush Surana, show me your schematic. You have completed your
Yes,
schematic, right?
No, sir.
Okay.
Sir,
So who have completed schematic? So please, if you have completed your schematic, show it.
sir, I've, sir,
You took my name earlier.
Okay. So you are present? All right. Okay, so anybody, if you are ready with the schematic, just turn on your camera and show your schematic to me.
Sir, is it visible?
Who is this? Adrija. Okay. It's visible. So let me see. A thick wall tube, stainless steel, 2 centimeter inner diameter, 4 centimeter outer diameter, or 3 centimeter layer of asbestos. Inside wall temperature given, outside wall temperature given. Okay. Okay. So you have drawn this. So what all are given and what you have to obtain?
We have to find the heat loss per unit length.
So mark those in that schematic. Write it down.
Okay, sir. So like I've written the temperatures and all.
Okay, not very visible to me because of the camera. Okay, anyway, it's fine.
Okay, sir.
Okay, anyone else want to show schematic drawing?
Sir, it's visible.
Who is this? Rahul Golda? Is this Rahul Golda?
Yes, sir.
No, it's not visible.
Sir, is it visible?
Just wait a minute.
Is it visible, sir?
Not yet. Okay, it's not coming. So let me start drawing this. So this is problem number 4. Tutorial 1. Problem number 4. So what it says that a thick walled tube of stainless steel, thermal conductivity given, with 2 centimeter inner diameter and 4 centimeter outer diameter is covered with 3 centimeter layer of asbestos insulation. So inner diameter is 2 centimeter. So this inner diameter is 2 centimeter inner diameter tube. Not tube, it should be called a pipe of stainless steel with 2 centimeter, 4 centimeter outer diameter. So outer diameter should be almost double of that. So this is the outer diameter. Okay. With 3 centimeter layer of asbestos insulation. So insulation is pretty thick. This is the asbestos insulation. If the inside wall temperature is 600 degrees centigrade, outside wall temperature 100 degrees centigrade. So this is 600 degrees centigrade and this temperature is 100 degrees centigrade. Okay. And the K is 19, K is 0.2. This K is 19. So this is K1 equals to 19 in SI unit. K2 equals to 0.2. Okay. Heat loss per meter of length. And also find the tube insulation interface temperature. So Q by L is being asked. So it is Q dot over L is what? And if we have a notation of T12, right? What was the notation for this temperature? T. T1, T2. So I don't see it. So maybe T12 is a good notation. This is material 1, material 2. So this temperature is T12 is being asked. All right. Good. So now this is, you have to make a plan. So the plan is that we already have an expression for Q. Ti, To are given. All these radius are given. Radii are given. Ro, Ri, R12 are given. Ho, Hi are not given. So our plan is that since the wall temperature is given, so that means wall temperature is known. So it's reasonable to assume that the convective resistances are very small. That means this convective resistance, these two convective resistances may be neglected. So this expression simplifies to this one, and we have been asked Q over L, so you don't have to worry about L, you can just pull L outside. So all these values are known. So all you have to do is to put the values here to get the value of Q over L. So it's a simple problem. Go ahead and get the value of Q dot L and then tell me what is the value.
So could you just repeat once again? I missed it.
Okay.
How do we calculate H?
H is not required because here the inside wall temperature and outside wall temperature, these two temperatures are given. And since these temperatures are given, so it's implied that someone was able to measure those temperatures, and it is reasonable to assume that this H, the resistances are not significant. So we neglect these two resistances. In another way of, yeah, go ahead.
Yes, sir, got it.
Another way of thinking is that you just, in this problem, you can think of this boundary condition as the outside temperatures are given, then this doesn't appear. But since we are reducing this, it's this is the slightly easier way to think. So get the value of Q dot by L and type in the chat box. Yes, Pooja Sharma's values are correct. Hold on. I think some decimal point is missing, or I have missed. I don't know. Some of the values come. Yeah, 680 is something. I also got 680. Make sure you get the value of 680 watt per meter. So even with the insulation, you will lose 680 watt. See, almost this close to more than half a kilowatt per meter length of pipe. A huge amount of loss, even with the insulation. Okay. So the temperature can also, so this comes to be 680 watt per meter. This is.
Sir, I'm still not able to understand how did we find R1, R2, R12?
So these all dimensions are given. So this is given as diameter 2 centimeter, right? So this is given as
2 centimeter.
yeah, 2 centimeter that. So put everything in SI unit whenever you have the opportunity. So 2 centimeter inner diameter. So this is 2 centimeter. So Ri is 1 centimeter. This is 1 centimeter, and this is
Ra is the radius. Okay, sir. Yes. Yes,
then
sir,
after
got
2
it.
centimeter here, 3 centimeters. This should be 3 centimeter. This should be 6 centimeter. Is that correct? I did that. 3 centimeter layer of asbestos insulation, 4 centimeter outside diameter, that means 2 centimeter. No, this is 1 centimeter, this is 2 centimeter. This is 2 centimeter and this should be then 5 centimeter. Okay. So make sure that you get the value correct. And now we can use these expressions. I think some of this part is missing. So anyway, I think you have this solution for T12. So solution here is T inside minus. So this is expression T12 equals to T inside minus Q by L by 2 by Q1. So this we obtain by when we solve this set of equation. I don't see that here, but when you solve this set of equations, we had this expression. So anyone has difficulty with this expression? Okay, I think most of you got it. It's an easy problem. Okay, so now let us see the how much resistance is present in the metal wall, how much resistance is present in the insulation. So just write 1 by Ui and write the term, the resistance corresponding to metal wall and resistance corresponding to insulator. And type the values here. So it's understandable, you see that very little temperature drop occurred in the metal wall. So metal wall resistance should be very less. That we understand, but just we want to put values to see the numerical values of those, because these are very important. For many cases, we will be neglecting the metal wall resistance. So I'm getting a variety of values for these two. I think the unit is giving trouble. So just make sure that you put everything in SI unit. So we have for metal, this is Ri. So ln R12 is 3 centimeter. 3 centimeter divided by Ri is 1 centimeter divided by K1 is 19 divided by Ri is 1 centimeter means 0.01 meter. And plus insulator is ln Ro is 5 centimeter divided by R12 is 3 centimeter. See, here I can happily put the centimeter values in logarithmic because they are in ratio, so they will cancel. But here I cannot put that. So K2 is 0.2 divided by, again I have divided by Ri. Ri is 0.01. So it should come.
Sir,
Yeah.
so that will be like it is not 3-2 na, because outer diameter for the metal is 4 centimeter.
Outer diameter is 4 centimeter. So outer radius is 2 centimeter.
Yes, sir. ln 2/1 and ln 5/2.
Okay, so it will be 2, yes. So it should be ln 2 divided by 19 into 0.01. So that is 0.3648. So zero point triple naught 3648, and here we have ln 5.3 divided by 0.2 into 0.01. So not 255. You see that we have almost 3 orders of magnitude difference. So 1 in 1,000. So huge difference in terms of resistance. So that's why you see that we neglect the metal wall resistance for many cases. Okay. Now this schematic itself showing an interesting feature of this cylindrical system. So that is called the optimum thickness of insulation. So if you increase the insulation thickness, of course some heat has to travel more distance in this way, but at the same time you see the heat transfer area is increased. The area from which the heat transferred, that is increased. So it's not guaranteed that always you will have less heat transfer if you increase the amount of insulation. That is because of this area increase. So in one extreme case, say suppose this insulation has a thermal conductivity just little less than this of metal. So actually you are not making much change in this surface temperature, rather increasing huge amount of area. So in that case you will have a lot of heat loss. So instead of decrease in heat loss, you may have increase in heat loss. So in other words, if you look at this expression, Q over L, which is a function of Ri, Ro, and R12. If you plot it as a function of Ro, if you plot in this expression, if you plot Q by L, which is a function of other variables, suppose we keep everything as constant and vary Ro, so we make it a function of Ro. And if you plot this variable Q by L as a function of Ro, you will see that it initially slightly decreases and then it increases. So sometimes it looks like plot looks like this, it may look like this, but there is most of the time there is an optimum thickness of insulation. Lower than that optimum thickness, you will have higher heat loss. Even if you increase the thickness, you will have higher heat loss because of increase in area. This increases because of increase in area. This increases because of increase in path of heat transfer. So this decreases because of increase in path of heat transfer. This feature is not seen for planar case. Planar case, no matter what is the thermal conductivity of the insulation, this always gives you less heat loss. But for a cylindrical system or spherical system, there is an optimum insulation thickness beyond which you increase the heat loss because of increase in area. Any question on this optimum insulation thickness? Okay, so what is this optimum radius? We can obtain by differentiating this expression and setting it to 0, and then we get the expression for Ro. So let us do that. So I need to rewrite this expression or write it as something. So we write Q by L. So we write Q by L equals to 1 over Hi Ri times 2 pi plus ln R12 Ri over K1 2 pi plus ln Ro over R12 So in this expression, we keep everything as constant. Ti, To constant, we won't change it. Ri is the pipe diameter, inside pipe diameter, we won't change it. R12 is the outside pipe diameter, we will not change it. Or all we are doing is that we are putting more and more insulation, so that is we are changing Ro. So the only variable here is Ro. So if we write dq over L dRo equals to So Ti minus To remains as it is. I have put it in that side, so this is -1 here. So we have a negative sign here. This entire square bracket thing go to -2. Then this is not a function of RO, this goes to 0. This is not a function of RO, this goes to 0. And this goes to 1 over RO over R12 times K2 2 pi. Okay. And this is RO to the power -1. So minus 1 by RO square. 1 by HO RO square 2 pi. Okay. So this has to be set to 0. This is the overall resistance. Overall resistance is never 0. So this cannot be 0. Temperature difference cannot be 0. So we can set this to be 0. So optimum is obtained by setting this to be 0. Or a condition for R optimum, RO optimum is RO over R12 R over R12 K2 2 pi equals to 1 over HO RO square 2 pi. 2 pi cancels. R12.
Sir,
Uh,
sir, in that expression, it should be multiplied by R12 in denominator.
yeah. That's right. So I just took this one. Now I have to differentiate this also. So numerator also will have 1 over R12. That's why R12 will cancel. Okay, so the R12 will cancel. So we'll have 1 by RO optimum equals to K2 over H0. Our optimum radius is H0 over what happened? 1 over RO. H0 over K2. Something is wrong because dimensionally it is 1 over R2 is here. K2 1 over RO optimum is K2 over H0, whatever it is coming. Should be dimensionally consistent. Yeah. So no, something is wrong here because see if you can push this RO.
Sir, in K2 by H0, there should be also R0 square in denominator.
Yeah. That's why I was wondering. So here R0 square denominator, so it goes R0 square optimum. So R0 square optimum is K2 over H2. Yeah, now it's consistent. K2 over HO. Okay. So this is the optimum R0 values. Now what people do is that if you choose a very small K2, that is the insulation whose thermal conductivity is very less. So you can put this R optimum even lesser than the outer radius of the pipe. Okay. So that means his optimum business is khatam. So whatever you insulation you put, it will always result in less heat loss. It will never go into. So the optimum is lesser than the pipe radius. Okay. So just think of this point. So that is normally you have to do so that you do not have such optimum beyond the pipe radius. So if you choose that insulation, that kind of insulation with such low thermal conductivity, it will always be result in lesser heat loss whenever you whatever insulation you put. Okay, so is the concept of optimum insulation thickness clear to everyone?
Yes, sir.
Okay. Now let us take a 5 minutes break and then we'll solve another problem. In the break, you can ask questions. So it's 11:53 here. So another 5 minutes, almost noon, will start.
Excuse me, sir.
Ah, yeah,
Sir, I have a doubt.
yeah.
Sir, this expression for R optimum, it is K2 by H naught. So
Yes.
by this can we conclude that it is R optimum is independent, means the Q by L for which it is minimum, it doesn't depend upon the thickness of insulation.
Um, Q by L is a function of RO. So there is no
But
doubt.
here we didn't consider about the thickness of insulation.
Thickness means the radius. Radius, higher radius means higher thickness.
Actually, thickness is RO minus Ri, right?
Yes, Ri is common. So Ri is constant. So it's not Ri, it's R1 to say. So
yeah, R12.
R12 is
So
constant. So higher
considering
R,
R12 constant, we have calculated, right?
yes, R12 is constant because this pipe is constant. We are not changing the pipe. We are just changing the insulation thickness.
Okay.
Okay. So let us resume. And we'll start with solving the last problem of first tutorial. Spherical thin wall metallic container. So problem number 5 of conduction tutorial 1. Please go ahead, draw a schematic. Understand the problem, draw a schematic. Ankit Verma.
Hello. Yes, sir.
So get ready with your plan. In a few minutes, I will ask you, and you have to show me your plan and schematic.
Yes, sir.
Yes, show me the schematic and plan.
Yes, sir. Wait, sir. I am trying, sir.
Okay.
Sir, just wait for 2 minutes.
Okay, all right. Okay, so anyone is ready with the schematic?
Is it visible, sir?
Snehbandhu Singh.
Sir, is it visible?
Yes, visible. थोड़ा वो बैकग्राउंड ब्लर किया हुआ है, उससे इस कारण प्रॉब्लम हो रहा है.
No, sir.
No, still focus is a little bit problem. Okay, I can see a little bit. I cannot read those letters, but it's okay. I can see you have drawn the sphere and made the dimensions there. Okay, what is the plan, Snehbandhu?
So the plan is to write like the total resistance and to find the like heat rate of heat transfer. The total resistance like for this spherical it is R2 minus R1 divided by 4 pi k R1 R2 like that way. And the convective resistance also that way.
So from where you get this expression for this R1 R1 minus R2 or something like that. So so did you derive that or you learned somewhere?
So I derived that now only.
Okay, all right. So yeah, the first thing is that the previous expression for Q, capital Q or capital Q dot will not work because that was for cylindrical systems. For spherical system, you need a fresh expression. So that you can write by writing a heat balance and then putting the convective boundary condition. Okay. So write down the expression for Q, the overall resistance, and the expression for Q. So let me do that here. So it's a spherical cell, and it says that spherical thin-walled metallic container with liquid nitrogen at 77 Kelvin. The container has a diameter of 0.5 meter and is covered with an evacuated reflective insulation. Thin-walled metallic container. It says a thin-walled metallic container. So we can neglect the metal resistance. So we'll not draw the metal here. So we'll just draw the insulation. So we'll assume that metal wall resistance is not important, and also the properties of metal is not given. And the thermal conductivity of metal is not given. So we can see that basically the metal wall resistance has to be neglected. So this side temperature is 77 Kelvin. And they also say that somewhere no temperature gradient exists in the liquid nitrogen. So in the liquid nitrogen, so the entire liquid nitrogen, entire thing is at 77 Kelvin. So we can say that this wall temperature at this end is 77 Kelvin. Other side, the air side convective coefficient is given, and the ambient air temperature is given 300 Kelvin. So ambient air temperature is 300 Kelvin. H is given. H equals to 20 watt something. H is 20 watt per meter square Kelvin. H is 20 given here. Insulation is 25 millimeter thick and its outer surface is exposed to this is 0.5 meters. So diameter is 0.5 meters. So radius is 0.25 meter. So Ri equals to 0.25 meter and Ro 0.25, and this thickness is 25 millimeter. That means 0.025 meter. So 0.275 meter. Yeah. So this is Ri and Ro. So is that thermal conductivity of the insulation is given?
Yes, sir. It is 0.0017.
Okay, 0.0017. So Ki equals to 0.0017. Okay. So the plan is that first we have to get the similar expression for this spherical case. Spherical case we can write over a spherical cell, and we can say that minus Ki times dt dr. This is the flux, r direction flux, 4 pi r square. This is the Q. Q equals to this. This has to be solved with boundary condition. Q equals to 4 pi Ro square H into TO minus T ambient. or this can be written as T at R equals to RO equals to so this is TO, this will be here, TA, this has to be TA, it should be minus, I don't know why it's coming, Q by 4 pi RO square H. Okay, it should be lower than this. So why I'm getting this one? Okay, that is because the heat flux direction is opposite. So in Newton's law of cooling, I have to put a negative number here. Otherwise, it will give unrealistic things. So this when I write H equals to TO minus TA, so TO minus TA, this temperature is lower than this temperature. So I am talking about R direction heat flux. So it has to be, if I am talking about this direction heat flux, negative R direction, so this is T surface, I have to put a negative sign here. Then it will be put a negative sign here and this will be consistent. Okay. Yeah, that's the Newton's law of cooling, we have to put an appropriate sign. So the heat flux is in the negative R direction. So TO is, no, it was correct. So why I'm getting this one? DTDR is positive, so Q is negative. And Q equals to, that is equal to 4 pi RO square area and heat flux. H into TO minus TA. It will be lower than 300 Kelvin. 4 pi R square minus K insulation DTDR. It's okay. So in Newton's law of cooling, we write this heat flux as this away heat flux as H times T surface minus T infinity. So this is direction away from the surface. So here it's written as H, T surface as TO, TA. So this is away from the surface. So positive R direction. This is positive R direction flux. And this is also positive R direction flux. Should be fine. So positive R direction flux, we write as a 4 pi R square H times T surface is TO minus T infinity. Okay, so whatever comes, that comes. So it says that TO, that is the surface temperature at R is RO, that is TA. So actually Q will come to be negative. That will take care of all these sign problems. So Q will be a negative number because dTdr is positive. That's why Q is a negative number. Okay, it's fine. So TO equals to T ambient or T infinity. So let me correct that also. There's T ambient. Okay, so this is the boundary condition. And this equation has to be solved with this boundary condition. So from here we get dTdr Q by 4 pi Ki 1 over R square T equals to minus Q over 4 pi Ki minus 2 minus 1 over R. That's C1. So at R equals to RO, T equals to TA plus Q over 4 pi RO square H equals to R equals to RO square H plus 2 minus 2 RO plus 2 plus Q by 4 pi Ki RO plus C1. So this C1 has to be substituted here. T equals to Q by 4 pi Ki R plus TA plus Q over 4 pi RO square H minus Q by 4 pi Ki RO. Okay. So then we get this T ambient is higher. T ambient minus T. So this is the temperature at any location. And now what we have to do? We have to get this Q by, so we have to get the, so there is no Q by L business. So we have to get the total heat loss. So this is the T as a function of R. All right. So temperature as a function of R. So Ti minus To. So I can write it in terms of I can now put the, I know this T ambient, I know Ti. So at R equals to Ri, so I can put Ti as So I can put Ti. So Ti equals to Q over 4 pi Ki Ri plus Ta plus Q over 4 pi Ro square H minus Q by 4 pi Ki Ro. All right. So from here, we can write it in a nicer form. Ta is known, Ti is known, Ri, Ro, everything is known. So that gives us Q equals to, let us see what you have obtained. Get the values of Q. So some of you completed this derivation before. This I just did it for this case. So Q equals to, I can now write it in a slightly nicer form. So T minus Ti. So you can write so Q times one over this is a convective resistance. This is a conductive resistance. So Q will come negative, as I said, if you put Ta minus Ti, or Q equals to Ta minus Ti times the inverse of this resistances. Okay, now let us see what are the values we are getting. Yes. So how much joules are they? You're fine. Yeah, correct value. Yeah. Okay. Some more people please complete and tell me what is the value. So this problem involved a little bit of derivation and then providing the values. Okay, all right. Now let us move towards our little bit elaborate discussion on the relative resistances. So like this, you can write, so I have seen that for this thick tube with both convective resistances inside and outside, we can write that Ti minus To equals to Q times 1 over Hi Ri 2 pi L plus 1 over Ho Ro 2 pi L plus ln R12 over Ri K1 2 pi L plus ln Ro over R12 divided by K2 2 pi L. So this is our expression for overall resistance. Now you can see that it has this inside convective resistance, outside convective resistance, the conductive resistance for layer 1, conductive resistance for layer 2. And you have also seen in this spherical tank problem, we neglected the metal wall resistance by saying that this metal wall is thin enough. So that is also clearly visible in this expression, because if Ri and R12, these are closed, no matter what this thermal conductivity is. So irrespective of the value of thermal conductivity, it is very important that if the wall is very, very thin, irrespective of the thermal conductivity, you can say that this wall resistance can be neglected, because R12 is almost equivalent to Ri. So in that case, this logarithmic term is 0. So this resistance goes to 0. Same for the second layer. If second layer has R outer is almost similar to R12, then again this resistance will go to 0. Even whatever the thermal conductivity, doesn't matter. Okay. Another way this resistance can be 0 even when R12 is not almost close to Ri, is the thermal conductivity goes to a very large value. So it's also possible that the thermal conductivity goes to a very large value. So in that case, R12 may be much, much greater than Ri, but Q1 almost going to infinity. In that case also, this term goes to 0. So it is not that you have to have a very thin wall or you have to have a very large thermal conductivity. Any one of these conditions, if met, they will give rise to a very negligible resistance because of the metal. So that point is important. Now let us little bit elaborate on this point. So let us consider a pipe. Okay, so a pipe which is transferring heat to the outside. Now it's many cases the outside this heat transfer coefficient, this HO, is very low. HO is very small. That is because many time you are dependent on natural convection. For example, in a cold country, if you want to heat the room, you run steam through a pipe in the periphery of the room. You don't normally use fan or something. Just normal by natural convection, this hot air goes up and then heats the room. Inside you have a flowing steam which has very high thermal, very high heat transfer coefficient. Hi is very high, but HO is very low. So this is a normal scenario when you have a very high heat transfer coefficient inside, very high heat transfer coefficient in the metal, very high thermal conductivity of the metal, and maybe the thin wall as well, but the outside coefficient is very low. So in that case, you will see that because this is low, this resistance is very high. So this is called the controlling resistance. The resistance that is very high, that controls the entire resistance. And we have seen such a problem before, that this is 2 orders of magnitude lesser than the other resistance. So in that case, we have certain way to deal with that problem that we are basically trying to bring out by through a small problem. So now consider 1 meter length of a pipe. Ri is 10 centimeter. Ri is 10 centimeter. Inside heat transfer coefficient, Hi equals to 10. Ho equals to 1. That's what I was talking about. Neglect the metal wall resistance. Okay. So metal wall K is almost going to infinity. So metal wall resistance is neglected. Now tell me what will be the value of inside resistance? What will be the outside resistance using these expressions? Ri is almost same as Ro. So in this case, both conditions are satisfied. That is, Ri is almost same as Ro. What is the inside resistance and what is the outside resistance? Just type those values in the chat box. L is 1 meter. All values are given in SI unit except the Ri is given in centimeter. So 10 centimeter, 0.1 meter, you can say. Yes, correct. 0.159 and 0.00159. 0.159. So inside resistance will be low. So inside resistance will be 0.159. Yeah. Inside is 0.159 and outside is 1.59. So this is 0.159, outside is 1.59. All right. So that is expected. Now let us say that now we make this pipe very, very thick. Now we make this pipe very, very thick, and it's hypothetical pipe. So now I make this outer radius RO equals to 100 centimeter. K1 is again tends to infinity. So as we discussed that although RO and RI is not same anymore, but because K is infinity, we can again neglect the metal wall resistance. Now tell me what is resistance inside and resistance outside. Yes. So you know by now that because we increase the RO, so outside resistance now drop by an order. So the RS now resistance inside is 0.159. Outside is also again 0.159. Okay. So you see that overall resistance is now 0.318, whereas the overall resistance was 3.18. So you see that this overall resistance has dropped substantially without changing any heat transfer coefficient. Outside heat transfer coefficient is natural convection, whatever happening. You cannot do anything. But what you could do is that you could change the outside area. So to mitigate the low heat transfer coefficient in the outside, you could change the outside area. Okay. And thereby you could reduce the resistance by almost an order, and you could increase the heat transfer by almost an order. So you need to understand this very clearly. If you have any question, you ask. So the point I am making here is that although you cannot change the outside heat transfer coefficient because that is natural convection, whatever density difference is there, it's happening. But you can change the area. Whichever side has lower heat transfer coefficient, if you can increase the area of that side preferentially with respect to the other side, you can achieve higher heat transfer. And in this hypothetical case, we achieve that by making the tube unrealistically thick. 1 meter, almost 1 meter thick pipe wall. No one will be able to make that pipe, but this was effective. Practically, no one will make such a pipe. Rather, people will make higher area in another side by using fins. So this is how a tube will look like. So outside area we have increased by adding this kind of fin. So I'll show you some picture from this book. I think Leonhard has good pictures. So Can you see my screen? So are you able to see my screen?
Yes, sir.
Yes, sir.
Okay. So you see that these computer processors have these fin surfaces. Because other side, although there is a forced convection here because of this fan, but that is not enough. So they put fins. There are other nice picture of fin surfaces.
But we can't see the book, I guess.
So your
Okay.
is only visible that written part.
Okay. Just hold on. Now you can see the book.
Yes, sir.
So these are some examples of fin surfaces, fin arrays. These are computer processors. So and I don't know, the new processors might not come with such large fins, but these are fin surfaces for computer processors. So long ago when we used to assemble the desktop, so we used to take these fins and very carefully put this heat transfer thing on the processor. Leonard has made fun saying that the Stegosaurus with that might have been cooling fins. I think this will give you a better idea of how these fins looks like. So these are cutout views of various kind of fins. So that type I have drawn is like this. So there are this kind of fins are also there. These are circumferential fins. These are also circumferential fins. So you see the tube inside, this is the outside. This actually shows very clearly. Okay, so if one side heat transfer coefficient is low, you increase the area of that side by adding fins. And the logic is clear from the previous toy example.
So can we say that the window air conditioner is an example of this finned? Like we have the fins on the back side of the.
Yes, there are fins. Car radiators, those are fin surfaces. Motorbike engine itself is a fin surface. The block piston that you see in motorbike, that has fins. And these fin surfaces, so if you go in cold countries, you will see that such fin surfaces runs on the side of the rooms. Okay, so this is the fin surface. And our next venture will be to analyze this kind of finned surfaces. And we have little time left today to start that. So we'll not start that today. So let me see if we can discuss some small part from that. Yeah, okay, we can discuss a little bit of that. See, fin surface, so the example that we are talking about in this, we assume that K1 is infinity. So that means, so whatever surface you add, those are at wall temperature. So if this is T wall, so for this T infinity case, this is at T wall. This is K is infinity, so this is also at T wall. So as much surface as you can add, that will increase the heat transfer rate. But practically this K is not infinity. So if you add fin, so heat has to transfer in this direction, and that means there need to be a gradient in temperature. So if this is TW, this is also TW for finite K. K is finite. If K is finite or small or moderate, so in that case there will be a gradient in temperature. So that means temperature from T wall, it will gradually change, and after certain distance, certain length of the fin, it will reach something very close to T ambient. So there will be very little or no heat transfer from the fin to the ambient for that cases. So a fin is efficient only up to a certain length. So we have to analyze a fin for its efficiency. So this fin, if everything is at TW, if I give it a fin of a given length L, an ideal fin will have everywhere temperature as TW. Here also TW, here also TW. So total amount of heat transfer from an ideal fin is H times TW minus T ambient times area of fin. This is the Q max. But for a real fin, it will be lesser than that. How much will that be? That will be the total amount of heat that is pushed through the base. That much heat is gone to the surrounding by convection. So that is area of base times minus K times dt dx at x equals to 0. This is x. Okay. So this is Q actual, and an efficiency of the fin is defined as Q actual divided by Q max. So if you know the efficiency of a fin, you'll be able to calculate what will be the amount of heat transfer. So this is a little preliminary point. You can reflect on that, think of that, and you can ask questions. We have still 2 minutes left, but I will not start the analysis of fin today. We'll do it next week. But what I want you to do is today is the idea and concept of fin to be clear. That why there is a need of a fin. That one side heat transfer coefficient is less, that can be compensated by increasing the area of that side. And an engineering way to increase one side area without changing the area of another side is adding fins. And next concept is the efficiency of a fin. An ideal fin will have the same temperature everywhere, so that it can transfer maximum amount of maximum amount of heat. For a real fin, there will be temperature drop along the length of the fin, and after a certain length, the temperature reaches close to the ambient temperature. The fin is not effective, so you can add more area, that will not do any good. So that gives a lesser than ideal heat transfer, and the actual heat transfer is obtained by counting how much heat is pushed through the base, because it's a steady state condition we are considering. So whatever heat we push through the base, that will be transferred, and the actual heat that pushed through the base is heat flux at the base from the Fourier's law times area of the base, and ratio of this actual heat transfer and maximum heat transfer is the efficiency of a thing. These are few small concepts which I want you to understand. Go ahead, if you have any question, ask. Okay, so lecture ended. So if you have question, you stay, ask question. If you don't have question, you feel free to leave.